so we can go ahead to start. So anyone's ready? Let's go for it.
Can I start?
Yes.
Okay, thank you.
I noticed you leave class very early.
Who, me?
Yeah.
Oh no, my internet on Thursdays, because my brother is also on his computer, snaps out.
Okay.
So I always leave and then come back and leave and then come back.
I see. Okay. All right.
Okay, can you see this?
Yes.
Okay, good. So I'm doing question 50 of chapter 3. Each of two identical in appearance cabinets have two drawers. Cabinet A contains a silver coin in each drawer. Cabinet B has a silver coin in one of its drawers and a gold in the other. A cabinet is randomly selected. One of its drawers is opened and a silver coin is found. What is the probability that there is a silver coin in the other drawer? So I drew a little photo. So this was to me A and B. They're supposed to be identical. They're pretty identical. And then B has one different colored coin. Okay. So then cabinet A I said was A, cabinet B is B, and silver is S. So the chances of getting cabinet A, if I was to choose randomly, is just 1 out of 2, and so is B because there's only 2 drawers. And then if we open A, it's 100% going to be a silver coin. And if we open B, it's only 50% going to be a silver coin. So I used the formula, I think it was Bayes' formula, and I insert it into the equation. So 1/2 times 1 over 1/2 times 1 plus 1/2 times 1/2. And that got me 2 over 3. So the probability is 2 out of 3 that there's going to be a silver coin in the other drawer.
Nice. Clear.
Thank you.
Okay, who's going next?
Hi, Professor.
Hey, Catherine, yes.
Okay, I'm presenting question 60. So in a class, there is 4 first year boys, 6 first year girls, and 6 sophomore boys. How many sophomore girls must be present if sex and class are to be independent when a student is selected at random? So I let X equals to sophomore girls, and event F is freshman, and complement of F is sophomore, G for girl, and complement of G is boy. And I made a little chart just to see it. So we have 6 first year girls, and then we don't know how many sophomore girls are there. So we got 6 plus X. And for boys, freshman boys is 4, and the sophomore boys is 6. We got a total of 10. So when we set up the probability, since we know that if sex and class are to be independent, so we set the probability of the freshmen and the girls equals to probability of freshmen times probability of girls. I set it up as proportion to solve. 6 over 16 plus x equals to 10 over 16 plus x times 6 plus x over 16 plus x. And then we do a little math in here. That leads us to 9 sophomore girls.
Oh, Catherine.
Yes.
Are you muted? Oh, okay.
No, I'm not muted.
Okay. I couldn't hear you.
Oh.
Are you finished?
Oh yeah, I finished speaking. Is my voice
okay.
not good?
Okay. Hold on 1 second. Yeah, I was only up to here. I was waiting. Oh, okay. You just skip this because this is just a linear equation. I see. I see your point.
Yes.
Great. Yes. Looks so great. Looks so good. Anyone has any questions? Very nice.
I got question 32. The question is a
Okay.
bit long, so it says that a box is randomly selected.
Hold on. How it's gone?
Huh?
It's gone from my
Oh,
screen as well.
I just clicked it by mistake.
Okay.
Right. Can you see it now? Wait,
It's popping up.
is it popping up? This one?
It's
Second.
oh, it's gone
Show
again.
application. This one. Yep. Okay, I'm going over question 32. Since a box is randomly selected, so the probability of choosing box 1 and box 2 is the same, it's a half. And then BM is for black marbles, and B is for the box, W is for white marbles. The first question asks what is the probability of a marble is black. The probability of a marble is black is the probability of the two box and probability of the black marbles. So by set up like this one, the probability of black marbles in box 1, and then the marbles in box 1, plus probability of black marbles in box, choosing of black marbles in the box 2 and probability of box 2. And plug in the numbers, I get is 7/12 as choosing a black marble. And the second question asks what's the probability that the first box was the one select giving that the marble is white. What I saw is this one, the probability of box 1 and it's white over probability of white, and then come over here, sets up probability of white in box 1 and probability of box 1, and then we don't know that the probability of white, so 1 minus the probability of black marbles, which is here, and then plug in to get 3/5.
Great. Great. Anyone has any questions? Very clear. Okay. That's how.
Can you see my screen?
Oh, hold on one second. I'm updating our slides for presentation so I won't forget. Yes.
Okay, this is question 62. A simplified model for the movement of the price of a stock supposes that on each day the stock price either move up 1 unit with probability p, or move down 1 unit with probability 1 minus p. The changes on different days are assumed to be independent. So for the given, we have even increase or even decrease. For the even increase, we have possibility of p, and decrease is 1 minus p. And then for part A, what is the probability that after 2 days, the stock would be at its original price? So we have two possible cases, either first day increase, second day decrease, or first day decrease, second day increase. And since increase and decrease are two independent events, we can rewrite the probability of increase decrease to be probability of increase multiplied by probability of decrease. So we have p times 1 minus p. And then since there's two possible cases, and we multiply by 2. That's for part A. And for part B is what is the probability of that after 3 days, the stock's price will have increased by 1. unit. So we have 3 possible cases: increase, increase, decrease, increase, decrease, increase, decrease, increase, increase. So for the similar logic from here, we have p times 1 minus p and times 3 for part B. For the part C, we have given that after 3 days, the stock price has increased by 1 unit. What is the probability that even out on the first days? So we have probability of the first day is increased given the result from the part B. And then we just extend it, and we have the first day is increased interested the result from part B. So among those 3, only those 2, the first day is increased, and then divided by the probability from part B. And then we have those. Once we simplify, we got 2/3.
Great. Only one thing. Okay. If you want to call it probability of B, you could make a notation, make this one, the B part equals to P of B. Make the notation. Then you can use it in C.
Okay, got it.
Okay. Great. Thank you.
Thank you.
Hello, Professor.
Oh,
Hello. So I'm presenting question 42. Please consider a sample size 3 drawn in the following manner. We start with an urn containing 5 white and 7 red balls. At each stage, a ball is drawn and its color is noted. The ball is then returned to the urn along with an additional ball of the same color. Find the probability that the sample will contain exactly 0 white balls, 1 white ball, 3 white balls, and 2 white balls. So we have given 5 white and 7 red balls, total 12 balls. So question A asks for 0 white balls. So 0 white balls is also equals to probability of all 3 balls are red, because as we have 3 drawn over there. So probability of drawing a red ball is 7/12. The 7 over the total balls. The question says that the ball is then returned back to the urn along with an additional ball of the same color. So the total red balls is gonna be 8 when it's gonna draw second time, and the total number of balls gonna be 13. 12 plus 1, 13. So the second time probability of second time ball drawn red is 8/13. Same thing for the third time when the ball is gonna draw. So probability of 0 white balls is gonna be probability of red, 3 reds. All 3 balls are red. So we're just gonna multiply their probabilities. And question B asked 1 white ball. So we have these 3 possible cases. We're gonna have in the first row, we're gonna have 1 white ball, and then red, or it can be in the second row, or it can be in the third row. So probability of white is 5/12, 5 white balls over the total 12, multiply 7/13, 7 is the red balls, and the over 13, we're gonna add additional ball in the second row. So it's gonna be 12 plus 1, 13, and then the third time is gonna be 13 plus 1, 14. And then we're gonna add another red ball to the third time. So 7 plus 1 is gonna be 8. We're gonna do the same process for these 3 cases, and then probability of exactly 1 white ball is gonna be the addition of these 3 probabilities. And the probability of 3 white balls gonna be same like the probability of we have done in the probability of 3 red balls. It's gonna be 5/12 times 6/13 times 7/14. Each time we're gonna add an additional ball of same color. And 2 white balls, question D is gonna be, so we can have these 3 cases. First 2 drawn can be white, and it can be first time white and then red and then white, and then third time it can be first time red, and then the other 2 can be white. So yeah, the probability of exactly 2 white balls gonna be that. Yeah, I'm done, Professor.
Okay, great. Very clear. Very
Thank you.
nice. Thank you. Okay, I'm trying to find Zakia's name, give her credits. Zakia. Oh, yeah. Okay.
Okay, this is problem 74. We are given there's a 50-50 chance that the queen carries the gene for hemophilia. If she is a carrier, then each prince has a 50-50 chance of having hemophilia. If the queen has had 3 princes without the disease, what is the probability that the queen is a carrier? So for the first part, we use Bayes' formula. So for the numerator, we flip the variable that we are conditioning on. So initially we condition on that the first 3 children are negative. And so the numerator, we have to flip the condition where we condition on the queen having hemophilia. And for the denominator, we use the law of total probability, where we again flip the condition we're conditioning on, which is conditioning on the queen having hemophilia. And we also add the condition where the queen does not have hemophilia. That's how we get the summation. And once you plug in the values, which is 50% chance that the child has hemophilia, if the queen has hemophilia, we multiply that 3 times for each independent event of a child. That's how you get 1/2 multiplied by 1/2 3 times. And for the event where the queen does not have hemophilia, then the probability of the children not having hemophilia is 1, because she doesn't have the gene. And the probability of the queen not having hemophilia is 1/2, which which was given. So once we plug in the values, we get 1/9 chance the queen has hemophilia if the 3 children are negative for hemophilia.
Nice.
There's another question. Part B is if she has a 4th child with hemophilia, or what is the probability that the 4th child has hemophilia, given that the first 3 children were negative? Again, we use the law of total probability to convert the numerator, where we sort of flip the condition that we're conditioning on, and then also remembering to sum the complements that we condition on, which in this case is whether the queen has hemophilia or doesn't have hemophilia. So that's how you get the conversion of both the numerator and denominator. And so for the numerator, we have the condition where the queen has hemophilia, which was 1/2 to the 5th power. Since each child was a 1/2 chance, these are just treated as independent events. So I guess the only tricky part is that when the queen doesn't have hemophilia, then the probability of a child having hemophilia has to be 0. So that's how I got the 0 additional part.
That is the second part.
Yeah. And then for the denominator, it was a similar process, except for the second part where it's 1 times 1/2. That's from the probability that all of them are negative, given the queen is negative. So that has to be a 100% chance. And then we multiplied by 1/2 because the probability of queen being negative is 1/2. So once we get all these values, we just get 1/32 divided by 9/16, which is 1/18 chance that the 4th child has hemophilia, given that her 3 children were negative previously. And that's all.
Very nice. Very nice. You can do this. Very nice. Anyone has any questions? All right. Thank you, Tom. Okay, let's see who's next one. We have all right, popping up.
Yeah, yes. Hello.
Hello.
Okay, so I'm doing chapter 3, problem 33. It's a long problem, so I'm not gonna read it completely out. But first, I started out by denoting all the events in the problem. Pretty much we have doctor calls, heads, tails, good news, and bad news.
Just quickly, just give us a little brief. How's the question set it up? Yeah.
Oh, okay. So pretty much Miss Akina instructs the doctor to, I'm sorry, let me just back up. So I'll just read the problem then. So Miss Akina has
Okay.
just, sorry?
Go ahead.
Okay. Miss Akita has just had a biopsy on a possibly cancerous tumor. Not wanting to spoil a weekend family event, she does not want to hear any bad news in the next few days. But if she tells the doctor to call only if the news is, she tells the doctor to call only if the news is good. Then, if the doctor does not call, Miss Akina can conclude that the news is bad. So, being a student of probability, Miss Akina instructs the doctor to flip a coin. If it comes up heads, the doctor is to call if the news is good and not call if the news is bad. If the coin comes up tails, the doctor is not to call. In this way, even if the doctor doesn't call, the news is not necessarily bad. Let alpha be the probability that the tumor is cancerous. Let beta be the conditional probability that the tumor is cancerous given that the doctor does not call. Okay. And so what we're looking for is what should be larger, alpha or beta. And then we want to find beta in terms of alpha. And then prove the answer in part A. So I started out by listing all the events. The doctor calls, heads, tails, good news, and bad news. And so the givens we have for alpha is the probability of bad news, beta, the probability of bad news given no call. Then we have the probability of calling given tails, which is 0 because I'm not going to call. The probability of calling giving heads and bad news, again, it's going to be 0. That's a no call. And the probability of calling given heads and good news, which is going to be 1, which means the doctor is going to call. So my reasoning for part A is that all bad news is going to be a no call. So no matter what, if it's bad news, the doctor is never going to call. There is some good news in no call, which is that if the doctor flips a tails, it could be good news, but the doctor still won't call. So there is some good news there. So the probability of not calling is going to be greater in good news. So what this means is that because there is, so the probability of there being bad news given no call is going to be much more likely than the probability of being bad news, because if the doctor can flip a coin and he'll get tails, it could be that the doctor has good news, but the doctor still will not call.
Right.
Because not calling, because all bad news is in no call, it's going to be much more. It's going to be higher probability. Does that make sense?
That makes sense, because the probability of bad news is lower than the probability no call is bad news, because no call could have good news too.
Yes. And so for part B, I just laid out the beta in terms of alpha.
What is the second question? Oh, find the beta in terms of alpha. I see. Oh, hold on. You're equaling those two.
I'm sorry?
Bad news and no call, because like bad news and no call is bad news. Okay. Yes, makes sense. Yeah. Okay, so beta equals to alpha divided by probability of the complement no call, probability of no call. Okay. Anyone has any questions? Great. I like the analysis at the very beginning. Yeah. Looks like a very complicated question, but once you have this logic set it up, event set it up, and you have this logic. Great, good job. Thank you.
Thank you.
Okay, anyone else? Oh, right. Yeah, oh, Rob, yeah. And I want to listen to. Yeah, go ahead, please.
I don't know why the right side of it cut off, but it's not important. The question is, there's a 30% chance that A can fix or bust a computer. And if she can't, then there's a 40% chance that her friend B can. So if event A is her fixing it, and event B, given that A can't, is 0.4, yeah, that's what's cut off on the right. Probability of her friend B fixing it, given that A cannot, is 0.4. And the probability of her fixing it, A, is 0.3. So the first question is, find the probability it will be fixed by either A or B. And to find that, you have to find the union of these two. Well, you're given probability of A, 0.3. And to find the probability of B fixing it, you have to find the average of B fixing it given that A cannot, and given that A can, or A did fix it. So the probability of B fixing it given that A cannot is 0.4 given in the problem. And the probability that A cannot fix it is 0.7, which is the complement of 0.3. Plus, oh, sorry. I don't know why there's two pages. Plus the probability of B fixing it, given that A can, is 0, because if A fixes it, then B does not need to do anything, times the probability of A fixing it. So that multiplied is 0. So you have 0.4 times 0.7, which is 0.28. So, and 0.28, that's the probability of B fixing it overall. And if you're adding that to probability of A fixing it, then the probability that will be fixed by either A or B is 0.58. And part B, if it's fixed at all, what is the probability that B fixed it? To find this, all you need is the probability of, given from the last problem, the probability that's fixed at all by anyone as a sample space, and then of that, the probability that B fixed it, which is 0.28 over 0.58, which is 14 over 29.
I see. If it's a fixed, what is the probability it will be fixed by B? Yes, okay, okay, got it. Okay, great. That's wrong. All right, so Red, right? You're going to present as well.
Yes, give me a second. I'm gonna share.
Okay.
Let me see the file. Okay, so I'm gonna share there. Do you see it?
No.
Okay.
This.
Stop sharing. Entire screen. Okay. Do you see it, right?
Yes.
Okay, so the question is 25. Maxuma goes to Charlie's to buy groceries and to Marcelo to buy meat. Charles gives tokens to customers 10% of the times they visit the outlet. whereas Marcelo offers give tokens to customers 5% of the times. Both outlets offer tokens to Maxuma. For every 5 visits to Charles, she goes to Marcelo once. Given that she's coming home with the token, what's the probability that she's coming from Marcelo? Okay, so I'm gonna use this formula. Just gonna use different notations. Let's C be an event of visiting Charles store. Then C complement will be the visiting of Marcelo store. Then let's T be an event of receiving a token from any store. So this the same formula the different notations is this. Okay. We had from the description of the problem the proportion of visiting Charles store, probability of visiting Charles store to probability of visiting Marcel store is 5 to 1. That's what we have. That's this part here. And then the proportion of having a token from Charles store to having a token from Marcelo store is 0.1 to 10% to 5%.
Sorry, hold on one second. What is the H? What's H? P probability of given event E of H. Oh, this is just formula. Oh, okay, okay. Okay.
Use the same form, but
okay.
I'd like
I was
to use
looking at
different.
Yeah,
Only C's and T's. Okay.
That's right. That's right.
So we have this part and we have this part of the formula. Now I can find this proportion. This proportion is this. It's a proportion of having a token from Charles store to having token from Marcel's store. It's equal to 10 because I put all numbers here, 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 and I have 10. So the probability of having token from Charles store is equal to 10 times more than probability than having a token from Marcel store. Okay, so now I have to find the probability that the token is from Marcelo store. So it's this.
Right.
So it's a proportion of probability of having token from Marcel store to the total with probability. That's 1/11.
Hold on a second. Hold on a second. Right. So you need to find the probability of a given token from Marcelo's store. And you're seeing this equals to probability of token from Marcelo's store over? I'm confused.
The sum of two probabilities.
By getting
probability of having token from Marcelo's and from Charles store.
Something's not right here. Look this one. Your numerator on the right equation equals to the left-hand side. You see your left-hand side? The equation is probability of given token, the token from Marcelo's store, right?
Yeah.
But then the right-hand side is, the numerator is the same. Something's missing.
Okay, so maybe this different notation should be. But that's the answer to the question. What's the probability that she's coming from Marcelo's?
What is the probability that she's coming from Marcelo?
Is 1/11. Because we know the.
No,
I know this proportion. I know this proportion. It's 1 to 10. If I know it's 1 to 10, so it's a.
No, I'm looking at only, maybe there's a typo or something here. You see this equation, can you see my mouse, my cursor?
No.
You don't see my cursor, right? You see, okay, so right behind, not 1/11, the beginning. probability of token from Marcello's store. You have equal to probability of token from Marcello's store over the token.
I see. Yeah, that's strange, and I see, but maybe I should use different notation for this.
Token from Marcello's store. That's a question, right?
But
Yes.
this I got from this proportion.
Given that
Because
she's
if
coming
we have it 1 to 10, so that means so it's 1 over 11.
Hold on a second. Let me see your second one. So probability of token from Marcello's store over. I'm just getting confused with this. You're saying, hold on, let's see this. Yeah, it is true given token from Marcello's store. So the probability of the token from Marcello's store equals to hold on, probability from Marcello's store. So you're saying you should, if you use a different notation, they should be fine. Probability of token from Marcello's store over the whole thing. Yeah, just don't use, yeah, do that. Okay, now it makes sense. Yes. Okay, great. Yeah, you finished, right? Yeah, nice. Yes, good job. Yes, nice. All right, so this is ayat. All right, and anyone else like to present or have any comments? You know what I figured out? I'm going too slow with our material. Hold on, did I open it? Not yet. We need to do a little bit faster, otherwise I won't be able to finish the syllabus. So I'm going to, so chapter 3, what's important is conditional, chapter 3 is very important. Conditional probabilities, independent events, Bayes formula, all right? And independent events. So I'm going to skip 3.5, all right? And this basically is extending to finite many, the independent events, the conditional probabilities, okay? So I'm going to finish 3 and jump to chapter 4. We're going to start talking about random variables. Otherwise, we won't be able to finish. All right, so chapter 4, talking about we're starting random variables. So in this chapter, we're going to talk about random variables. We're going to see the definition of random variables, discrete random variables. Discrete means can be counted, okay, countable. You could put 1, 2, 3, 4, 5 like that. We're going to talk about expected values. And if you want to go to gambling, you want to play game with your friend, you want to calculate the expected value, you know, what is your chance of winning? So it's very useful. Expectations, a function of a random variable, and variance, Bernoulli and binomial random variables, Poisson random variables. So basically different probability models, functions, okay, models or functions. Some other discrete expected sum of random variables, probability of cumulative distribution functions. Okay, let's see what are random variables. When experiment is performed, we are frequently interested mainly in some function of the outcome as opposed to the actual outcome itself. For instance, in tossing dice, we are often interested in the sum of the two dice and are not really concerned about the separate values of each die. That is, we may be interested in knowing that the sum is 7 or may not be concerned over whether the actual outcome was 1 or 6, all those possibilities, outcomes. Also, in flipping a coin, we may be interested in the total number of heads that occur and not care at all about the actual head and tail sequence that results. So these quantities of interest, or more formally, these real-valued functions, right, defined on the sample space are known as random variables. Right. Real-valued functions. So this is class 3.5. So I think all of you have taken vector-valued calculus, right? So usually all the functions we can put under the umbrella vector-valued functions. Basically, we're sending one vector from an n-dimension space to a vector in m space dimension. A real-valued function means we can send any vector in any n space to a real value, so which is a one dimension space, right? We're sending, so that's real value function. But I'm not sure that if this book is going to talk about a multivariable, right? If it's multivariable, we name a vector, and if it's a single variable, it's also vector, right? It's just one element. The vector has one element. I'm thinking this book probably talking about just one variable, but in general, real value functions can be, you know, sending a vector from n space to a real value to one space. All right, so we call this random variables. All right, so that's because the value of a random variable is determined by the outcome of the experiment. We may assign probabilities to the possible values of the random variable. Okay, let's see. Example 1a. Suppose that our experiment consists of tossing 3 fair coins. All right, why we put fair coins? Because some coins may not be fair. Fair means we get a 50% chance, you know, landing on head and 50% chance landing on tail. If we let y denote number of heads that appear, so the event is number of heads appear, and we call y the y. Then y is one. Then y is a random variable. Okay, taking on one of the values. It could be 0 heads, or 1 head, or 2 heads, or 3 heads in a row. So with respective probabilities. So probability of no head is probability of tail, which is 1 out of 8. Because each time it's 2 outcomes, right? Either head or tail. So if we tossing 3 times, 2 times 2 times 2, that's 8. So that's why it's 1 out of 8. So only one chance to get all 3 tails, 1 out of 8. If it's 1 head, so we could have tail head, tail head tail, or head tail tail. So that's 3 over 8. If you have 2 heads, it could be tail head head tail head, or head tail. That's 3/8 also. If it's all 3 are heads, that's only 1, so that's 1 out of 8. Okay, so we call y the random variable, and then y can be assigned 4 values: 0, 1, 2, 3, 0, 1, 2, 3. Okay, random variable. Okay, let's see. Since y must take in one of the values from 0 to 3, we must have probability of 1 equals to probability of union of all those probability of the possibilities from 0 heads up to 1 up to 2 up to 3 heads. So adding them all, it has to be 100%, which is indeed, right? Well, 1 out of A plus 3 out of A, that's 4 out of A. This 3 out of A, 1 out of A is 4 out of A, 4 out of A plus 4 out of A, that's 8 out of A, that's 1. Let's see this one, example 1b. A life insurance agent has 2 elderly clients, each of whom has a life insurance policy that pays $100,000 upon death. So Y, random variable now, be the event that the younger one dies in the following year. And O, be the event the older one dies in the following year. That assume Y and O are independent, right? Because one is young, one is old, they have to be independent. But also it's relative. How do you define young? How do you define old? Anyway, so we assume Y and O are independent. With respective probability, okay, probability of the next one, the young one is 0.05 given, and the probability of old one is 0.1. If X denotes the total amount of money in units of 100,000, right? Because the policy pays for this much, each one pays for this much. So X denotes the total amount of money in this unit that will be paid out of this year to any of those clients' beneficiaries. Then X is a random variable, right? So basically, how many gets. And it takes on one of the possible values of 0, 1, 2. Okay, because a life insurance agent has 2 elderly clients. Okay, each of whom has a life insurance policy that pays this much upon death. So that's why the money can be paid. So if X denotes the total amount of money be paid, so there can be 0 money to be paid, or one of the 100,000 to be paid, or 2 of the 2,100 to be paid, because there are 2 clients. So X is a random variable. So X can be 0. That means probability of no young, no old, right? So probability of no young, no old, not dying, right? So no one. So basically, no one dies, right? So no money to be paid. And one dies to be paid, and then this one can be young one, or this one can be old one, right? Or both of them both died, right? To be paid. Then we have this probability of young and old. This. So X denotes the total amount of money to be paid. So X is a random variable, because X is a variable because it can be assigned 3 values, 0, 1, 2. Let's see C. 4 balls are to be randomly selected without replacement from an urn that containing 20 balls numbered 1 through 20. If X is the largest numbered ball selected, then X is a random variable that takes. If X is the largest numbered ball selected, then X is a random variable that it takes on one of the values, 4, 5, up to 20. Because each out of 20 choose 4 possible selections of 4 of the 20 balls is equally likely. The probability that X takes on each of its possible values is up to, so I is from 4 up to 20. And the probability of X can be assigned from 4 up to 20, then probability of X to be I is I minus 1 out of I minus 1, choose 3. Then, because that's this particular one, right? How many ways to choose this particular one out of 3? Then, over the sample space, out of 20, choose 4. So this is so because the number of selections that result in X equals I is the number of selections that result in ball numbered I, and the 3 of the balls numbered 1 through I minus 1 being selected. So as they are, out of 1 choose 1 for this, out of I minus 1 choose 3, such selections, the preceding equations follows. Suppose now that we want to determine probability of X greater than 10. x greater than 10. So that could be 11 up to 20. One way, of course, it is to just use the preceding to obtain probability of x greater than 10 would be the sum of all those I from 11 up to 20 would be the sum of all those, right? However, a more direct approach for determining probability of x greater than 10 would be to use this. Let's see. Probability of x greater than 10 is 1 minus probability of x less than or equal to 10 equals to 1 minus out of 10 choose 4 divided by out of 20 choose 4. Right, this is neat. Yeah, this is a much neater way, where the preceding results because x will be less than or equal to 10 when the 4 balls chosen are among balls numbered 1 through 10. All right, anyone has any questions? Kind of obvious, right? Just to know the random variables, because before we have events, each event is corresponding, each notation corresponding to event, or just for specific one thing. But now random variables can be assigned with different values. Let's see this. Independent trials consisting of the flipping of a coin having probability P of coming up heads are continually performed until either a head occurs or a total of n flips is made. If we let x denote the number of times the coin is flipped, then x is a random variable taking on one of the values 1, 2, 3 up to n with respective probabilities, right? X equals 1, this is just the probability of x equals 2, x equals 3, so on and so forth. Then we can add up all those probability for all those. That has to be 1. Because each trial is independent, right? Probability, so P is the probability of a heads up with n flips. And X denotes the number of times the coin is flipped. It could be 1 flip, 2 flips, 3 up to n flips, and each one with its probability, right? Probability to get ahead is P, so on and so forth. Let's see this E. Suppose that there are distinct types of coupons, and that each time one obtains a coupon, it is independently of previous selections, equally likely to be any one of the R types. One random variable of interest is T, the number of coupons that need to be collected until one obtains a complete set of at least one of each type. Rather than derive probability of T equals n directly, let us start by considering the probability that T is greater than n. To do so, fix n and define the events A1 up to AR as follows. So each AJ is the event that no type J coupon is contained among the first n coupons collected. So J equals to 1 up to R. Hence, by the inclusion-exclusion identity, so probability of T greater than n. So remember, what is T? The number of coupons that need to be collected until one obtains a complete set of at least one of each type. So T greater than n is probability of the union of all those AJ j's, j from 1 up to r, or which is because each event is considered independent. It is independent of previous selections. So equals all this, then subtract the intersections. So this is a formula from early on, subtract the intersections. Now AJ will occur if each of the n coupons collected is not of type J. Since each of the coupons will not be a type of J with probability of R minus 1 over R minus 1 over R. Yeah, because none of them, right? None of them is a type of, is the same type. Okay, so we have, by the assumed independence of the type of successive coupons, probability of each AJ is this raised by n. So each one. Oh, yes, because there's n coupons. Yeah, there's n coupons. Okay. Also, the event AJ1 and AJ2 will occur if none of the first n coupons collected is of either type J or type 2. Thus, again, using the independence, we see that probability of AJ1 and AJ2 equals to R minus 2 over R raised by n, right? Same logic. The same reason gives all those, right, to this. And we see that for n greater than 0, probability of t greater than n is, so now going back to this, right, just plug into this formula. Is r times this minus this, but we have to multiply by r choose 2, out of r choose 2, out of r choose 3, then this is 3, so on and so forth, up to r of them, up to one of them, right, up to the last one, 1 over r. What is this? Anyway, to get something like this. Probability of t greater than n minus 1 is a probability of t equals n plus probability of t greater than n. And probability of t equals to n equals to probability of t greater than n minus 1. Oh, okay, this is rewrite the first one. Okay, I'm going to skip the rest. I'm going to skip this rest. Okay, 4.2, discrete random variables. A random variable that can take at the most a countable number of possible values is said to be discrete. For discrete random variable x, we define the probability mass function, probability of A of x, by this. Probability of A equals the probability of x equals to A. Again, random variables can be assigned different values. The probability mass function, probability P of A, is positive for at most a countable number of values of A. That is, if x must assume one of the values x1, x2, blah, blah, blah. So I could be 1, 2, blah, blah. Probability of x equals 0 for all other values of x. Since x must take on one of the values xi, so we have adding all the probabilities, because this is an infinite set, because countable set are infinite set, okay? You can keep counting 1, 2, 3, 4, you can keep going forever. So that's why you see this is I goes from 1 up to infinity. So all those equals 1. So this is, well, let's just keep this in our head, okay? Because this is dealing with countable sets and the infinite many. It's often instructive to present the probability mass function in a graphical format by plotting P of xi on the y-axis against the xi on the x-axis. For instance, if the probability mass function of x is Probability of 0 equals a quarter, 1 equals to half, 1. Then adding all those three, we do get 100%. So we can represent this function graphically like this. 0 get a quarter, 1 we get a half, 2 we get a quarter, or like a 2 we get a 1 out of 36, so on and so forth. This looks like a bell shape. Right. Let's see this one, 2a. The probability mass function of a random variable x is given by probability of I equals to c lambda raised by I divided by I factorial. I equals to 0, 1, 2 countable set where whole numbers. Okay, this is a whole number set where lambda is some positive value. Okay, so lambda is some positive value, and when lambda is some positive value. So be careful with this. This I can be 0. Find A probability of x equals 0 and B probability of x greater than 2. All right. So given this function, all right, given this probability mass function, and we want to find x equals 0, probability of x equals 0, and the probability of x greater than 2. Now, probability of greater than 2 we want to find is a complement, right? Because I can be, can be infinitely big. So we better find 0 or 1 than find a complement. So let's see. Since probability of adding up probability of all the random variables or values that equals 1, so we can do this, right? Because this is a probability mass function. And if we add all those and let I goes from 0 up to infinity, so that has to be equal to 1, right? And C is a constant. So C is a constant, we can factor out the summation sign. So we just have to deal with the lambda raised by I divided by I factorial. Now, so this we recognize series again. Remember the infinite series we learned in calculus 2 class? That's e to the x, right? So so this is e to the lambda, because our x in here is lambda. So lambda raised by I divided by I factorial. I goes from 0 to infinity. Infinite series that equals e to the x. So we have e to the lambda. So that's why this can be written as c times e raised by lambda equals 1. So which means c equals to 1 over e to the lambda. Okay, so hence then we can plug in, right? If x equals 0, x equals 0, we have e to the lambda, because we have c now. We have c now. We have e to the negative lambda times lambda raised by 0, I equals 0, divided by 0 factorial. That's just e to the negative lambda. Well, x greater than 2, we want to do 1 minus probability of x less than or equal to 2, right? Which means 1 minus equals 0, equals to 1, and equals to 2, minus those 3. Right? For each one we can calculate. For 0, we already have e to the negative lambda. For 1, we just substitute in it, we get a e to the negative lambda times lambda divided by 1, which is just e to the lambda multiplied by lambda. So get this. When x equals 2, we substitute this, we get a lambda raised by 2 divided by 2 factorial, multiplied by e to the negative lambda. Let's look at this. So you see, what do we get? We get a function in terms of lambda. So everything, so this, the probability is a function in terms of lambda. So whatever lambda is, right, is defined, the probability becomes a function. It depends on the lambda. Okay, let's see this. The cumulative distribution function f can be expressed in terms of P of A by, so F of A, we can use this, adding all the probability of X for all X less than or equal to this A. If X is a discrete random variable whose possible values are X1, X2, da da da, well, this is in sequence, then the distribution function f of X is a step function. That is, the value of f is constant in the intervals, and then takes a step or jump of size to the next level. For instance, if X has a probability mass function given by this, right? Probability 1 equals quarter, 2 equals a half, 3 equals 1/8, equals 1/8. Right? So we can graph the function, right? It would be a step function. So then this cumulative function f of A is cumulative distribution function, okay? For A less than 1, A less than 1 is 0, okay? A in between 1 and 2, quarter. A in between 2 and 3 is 1/2 plus 1/4, which is 3/4. Right? A in between 3 and 4, adding all those 3, 7/8. Or A greater than or equal to 4 has to be 1. Right? If we graph it, so that's a step function. Anyone has any questions? Okay, note the size of the step at any of the values 1, 2, 3, 4 is equal to the probability that X assumes at the particular values. All right, so I'm going to just talk about, I'm finishing here. So random variables, discrete random variables, all right. Next class, we're going to talk about expected values. We're going to calculate this. And I think we should have some good examples. Expected values are a very interesting topic. So you could calculate any, if you play some games, you can collect the data, calculate, your chance of winning. All right, anyone has any questions? When is homework 3 due? Let me see. So I give you 2 weeks from now. Should I give you 1 week? You want 2 weeks or 1 week? Oh, I already put March 1st. 3, let's see. March 1st. Okay, I'm going to give you 1 more week. So let's do 8th. Okay, I give you 1 more week to finish homework 3. Homework 4, let's see. All right, homework 4, I'll set up later. Okay, all right, great. Okay, so you get 1 more week to finish homework 3. Probably it's going to take us, let's see, let me see. So 1, 2, 3, 4, 5, 2 weeks, 2 or 2.5 weeks to finish chapter 4, or maybe I just use 2 weeks because some stuff I don't really have to talk about. Actually, let's go back to the very beginning. because I need to cover the syllabus. I cannot go too slow. Cannot talk about everything. So chapter 4. Hold on. Random. Oh, I need to spend a good amount of time for chapter 4. Because we're going to talk about geometric random variables, Poisson distribution. All those are important. Hypergeometric. Probably we're going to skip a hypergeometric. Negative binomial random. Zeta distribution. Because, you know, since we have random variables, now we're going up to functions. So we have probability models. Expected values and probability cumulative. Let's see, 5. 5 continuous random variables, very important concept. 5. So chapter 5 is important. Yeah, normal distribution, uniform random, normal, gamma, Weibull, Cauchy, beta, Pareto. I don't know how many we can cover this. This is 6 jointly distributed random variables. So we have a joint distribution. Independent random variable, some are independent, identical, gamma random variable, normal random, Poisson, binomial random variable, conditional, discrete case, conditional. Okay, some of them we don't really have to talk about. 7, explain the sum of random variables. Okay, I guess we're fine. We don't have, because we're not going to cover the whole thing. We just have to cover the syllabus. All right, we're good. I was a little worried. When we're going to have a midterm? Okay, so I'm thinking in March. Somewhere in March, we're going to have a midterm. So maybe when we finish chapter 4, all right, I'll let you know at least 1 week before. Okay, any other questions? Okay, you're welcome. All right, keep your good work. Keep up your good work. And for the rest of you, please try to present, all right? Okay, have a good night. Let me stop recording.